All right, so Boolean algebra. Let's start with Boolean just means like yes or 0 or 1, yeah, true or false. So why algebra? Let's look at it. So Boolean algebra uses numbers and arithmetic operators for logical expressions. So the value 0 is false, 1 is true. And for the operations like or, we use the plus sign, and the and operation, we use the asterisk or the multiply sign. So instead of just being 0 or 1, sometimes we can use variables like A, B, C, or X, Y, Z. So variable just means that it can take on either value, 0 or 1. So at the end of the day, the Boolean is either going to be true or false. So things will always reduce down to a single true value or a false value. So let's take a look at variables. So variables, as I mentioned, they can take on either value and they can be changed on input. So these inputs can be added together to make a larger expression. So for example, if you see this grid, you have function of A and B, where A and B are inputs. The operation is the or operation, the plus sign. So it's A or B. So this whole expression will evaluate to whether true or false, depending on what the values of A and B are. So let's take a look at some of these basic operations. The first one is a not operation. So not operation means that if I have variable A, if A currently holds a value 0, then not A will be 1. If A currently has a value of 1, the value becomes 0. So this is just a not operation. You might have seen it written like this. If depending on where you look, it can be written like A with a line over it. That's not A. Another way is A with an asterisk. This also means not A. So depending on where you see it, they can be written in both ways. And from your discrete math class, I believe you might also see it written like this. Okay? They all mean the same thing. It means not A. So whatever value A currently contains, when you put a not over it or change it to not, it's going to be the exact opposite value. The next operation is AND. So AND operation takes two inputs, A, B, and the expression evaluates to true when both are true. So I have value A and value B, right? So these are the four possible values of A and B, what's 0, 0, 0, 1, 1, 0, or 1, 1. Out of all these operations, only one of them is going to be true when both A is 1 and B is 1. And it's going to be false otherwise. So that's how A and B evaluate. So the AND operation can be written like this. It's also written like this. It's also written like this. All of these mean the same thing, is that A and B are two variables, and there's an AND operation between A and B. Okay? So hopefully for most of you, this should be a review, because I believe this is covered in discrete math. Okay, or operations. Also takes two inputs, A, B, except it's true when either A or B are true, or when they're both true. So when A is true or B, anything is true, any one of the inputs are true, the whole or expression will be true. Now, exclusive or, this you probably didn't see in your discrete math class. So this is more a computer science operation. So exclusive or is almost like an or, except you have an X in front, right? X meaning exclusive. So it's only true when either B is true or A is true, but not both. So exclusive, mutually exclusive. So either A is true or B is true, but you can't have more than one thing true. All right? And this symbol is written as a plus with a circle around it. Okay, so that's exclusive or. Okay, so these four operations that we covered, not, and, or, and exclusive or, these are the four basic operations in computer science that almost all computer processing is built on one or more of these operations put together. All right, you're going to see what I mean in the next few weeks as we build little logical circuits to do different things, and you're saying, oh, you combine and, or, and exclusive or, you're able to do a lot of stuff. Okay, all right, so let's move down to Boolean algebra. All right, so we mentioned that we use algebra to represent the and, or, and variables. So these are some of the laws that apply, but these aren't all algebra laws. These are Boolean algebra laws. So it builds on top of it. So for the first three that you see, commutative law, associative law, and distributive law, if you look at it, this should be right from your algebra class, right? Because it's the same. The operations are the same. Especially the commutative. It's A and B will give you the same result as B and A. So very important thing that we'll touch upon later is that it doesn't mean they're the same thing. It means that they will evaluate to the same result. Either they'll both be true or they'll both be false, but you're not going to have like one's true, one's false. So it means they will equal the same truth value, true or false. Okay. So this is not to mean that they're the same circuit. Oh, very, very important. All right. So the first three, if you've taken algebra, then you should be familiar with the first three laws. Now, the next one is where we start making things a little bit more different. That's our specific to digital Boolean algebra. So A or 0 equals A. So you might think of, oh, A plus 0 is A. That makes sense. All right. Well, A times 1 is A, and 1 is also A. That makes sense. So what doesn't make sense, where the similarities break, is here, right? A or 1 is 1. Then what happens to A? Well, remember, you're not really, this is not addition. This is an OR operation. So when you have an operation like A or B, right, 0, 0, 1, 1, this is just the truth table for an OR operation. So in this particular highlighted, A or 1 equals 1. So these are the two rows where A is 1. I mean, B is 1, right? So notice that when B is set to 1, the result, whenever B is set to 1, notice the result is always 1. It doesn't matter what A is. All right. So this is just a way of saying that A or 1 can be reduced down to just 1 by itself. And I use the keyword reduce there, because if you look at all the remaining laws on here, there's less things to the right than there are on the left, because this is for the purposes of reduction. Remember, going back again to your algebra days, one of the homeworks that happen like almost every single night is they give you very large expressions, and it's always, please simplify, right? So that's essentially what we're trying to do. So a lot of these laws are used for the purposes of simplifying a larger expression down to a smaller one. Okay. So identity, let's move on. Complement. Complement just acknowledges A and not A equals 0, or A or not A equals 1. So these can be very easily proven just by using a truth table again. Let's do the A and B. 0, 0, 0, 1, 0, 0, 1, 1, 0, 1, 0, 1. Okay, so if we're trying to prove this one, right? So essentially this is saying we're A and something that's not equal to A, so they don't have the same value. So these are the only true rows where they don't have the A and B don't have the same value, the two inputs. So notice they're always 0. So whenever you have A and something that's the opposite of A, it always reduces to 0. So the next one you could probably prove to yourself, but A or not A will always reduce to 1. Now, idempotency, this is also something that's important, is that if we look at it, it says A and A is A. Well, again, very important. This is not addition. This is saying that when your two inputs are the same, like here and here, notice that if A is A, whatever A is, and you do an AND operation with another A, which is the same value, you'll equal the same value. So 0 and 0 will give you 0. 1 and 1 will give you 1. Okay? So again, this is just a way of reduction. The next thing is double negation. Double negation is intuitive, right? So it's not something. So you negate it once and you negate it again, it goes right back to what it was originally. De Morgan's should be something that was covered in your discrete math class. So De Morgan's is just two equations that show you how to convert from AND operations to OR operations, back and forth. Okay, so we'll leave that alone for now. Boolean algebra laws. All right, so some additional laws, but these are really theorems, more for simplification, is that these can be tested using a truth table. But all of these are for purposes of reduction, is that you take combinations A and B, or A or B, or some knots. All of these are used for reducing. Notice everything on the right is always either single variable or two variables. So these are ways of reduction. Okay, so why do we need to reduce things? Well, let's start off with a problem. Looking at this expression, A not A, B, C, or A not B, C, or A, B not C, or A, B, C. It looks very compact, but how many operations are in this expression? So think about this. I'm going to break it down. How many AND operations? How many OR operations? How many NOT operations? Okay? And how many exclusive OR? These are our four main operations. I want you guys to look at this, spend a minute or two, look at it, and figure out how many of each. I'm going to actually grab a cup of water. I'll be right back. Okay, guys, I'm back. All right, so looking through this, how many AND operations? Well, let's do an easy one. How many OR operations are here? Anyone? How many OR operations?
3.
3, good. All right, how many NOT operations are here?
3.
3. And how many AND operations?
8.
8, right? Everyone see the AND operations? Remember, in between every one of these guys, you have AND operations in between them, right? You don't have to, there's several ways of writing it. It can be written as A, B, C, or it can be written as A dot B dot C, or it can be written with asterisks. They all mean the same thing. It means that there's an AND operation. So there's 8. So there's a total of 14 operations here, okay? So why is that important? It's when a computer processes an expression, it performs one operation at a time. So there's 14 operations here, which means that a processor has to perform 14 separate operations in sequence. Well, arguably, let's just keep it simple for now. Say it's in sequence. Eventually, you might have parallel processing, but for simplicity's purposes, there's 14 operations here. Okay, so a computer wouldn't just come in here and do boom, do all 14 in a shot. You know, it might have to go through 1, 2, 3, 4, sequentially go through 14 operations. So 14 operations, you know, it is a lot, right? But the question is can this be reduced? Can we get the same result without performing as many operations? And the answer is yes, we can. So how do we do it? So let's start off with this expression that we have at the top, right? We have this expression. So using the algebra laws from a few minutes ago, we start out with distributive where we factor out BC, right? So that's what we're doing here. We factor it out, and then we use identity, this expression A or not A equals 1, and we change that, okay? And then we apply another identity, 1 and A is equal to A, to get rid of the 1. So now I have BC, and now I have to distribute B in here, right? Factor it out. And once I do that, then this is one of those simplification theorems to reduce it again, right? And then I distribute BC into here, and these two are done. Now I look at the other side, and I want to factor out A. And then I perform the simplification theorem again, and I get this, and I distribute A in here, and then I rewrite it around, and I end up with this expression at the bottom. So this expression at the bottom is simplified. So how many operations do you see in this expression at the bottom?
5.
5, exactly. So we went from 14 down to 5. Okay, it's almost 1/3 the number of operations. We'll get the same result. So this is sort of like optimizing the problem. So when we talk about hardware and making things faster, right? So there's 2 ways of making your program faster. One is by throwing more hardware at it, right? That just means given the same program, if I put a faster processor that just runs at a more clock speed, more processes per second, it'll get done faster. That's one way of doing it. The other is keep the same hardware and you optimize the software side of it. Optimizing software meaning you're reducing the problem that's being asked. Like for example, in this case, instead of 14 operations, you're getting the result in 5 operations. So this is almost 3 times, right? Divide by 1/3. So this could be 3 times faster. So instead of making hardware 3 times faster, you just reduce the problem by 1/3 and you still got the same result. So does anyone understand the importance of this? Is that speed is done in 2 directions. One is the hardware and the one is optimizing the software. They both will give you the same end result, is a faster experience and faster processing or faster answer. Okay, does everyone understand that? Why you want to do this now?
Yes.
Yep.
All right, good. All right, so now that we understand less operations is good, now we might want to ask, well, how does this operations look, on a logical circuit? And the answer is our next slide. The AND operation is represented with the symbol. So the way it's written is A, your inputs would have drawn in little boxes, A and B, and then this would be your AND gate. And the result is usually written in a little circle, okay? So A and B, A is a variable that goes in, B is a variable that goes in, and that semicircle, that is called an AND gate. So that AND gate will process this truth table that you see here. And it's going to output either 0 or 1, depending on the inputs of A. Whatever A and B are, those are the 4 possible inputs. This is what the AND gate is going to output. Okay? Same thing with OR. With OR, it's written like, it's like an arrow, right? Arrowhead and an output. And the NOT is just one input. A comes out and then has a circle at the end of it, and then this is the output. Okay, so one thing is not on here is exclusive OR. The exclusive OR gate looks like this. It looks like an OR gate, except there's two lines or 2 bars toward the base of the gate. Okay, so that's exclusive OR. Okay, so this is drawing a single gate. When you have more than one gate, that's where you have a circuit. Okay, so let's draw some of these circuits. So A or B, so circuits are by default, when all the gates are the same, you go from left to right. Okay, so these are 2 OR gates. So it's written as A, I have 3 inputs, A, B, C. All right, so we start from left to right. If all the gates are the same, then we go from left to right. So this A or B is first. We have an OR gate that connects them. And then once that's done, we have another OR gate that connects the result to C. And we're done. Okay? All right, so that's the first one. The second one, actually, let me copy this into our whiteboard just so I have more room to draw this.
Professor, are you on an iPad right now? Or
No, I'm on my laptop.
no, because you're really good at drawing. I'm just wondering if you're using like a stencil. Just
No, I am using a stencil. I have what's this thing called? ThinkPad. It's a ThinkPad with a screen that you can draw on.
oh, cool.
Yeah, the Apple's nice, but it doesn't run some software that I need to run. So I looked at it, but this is actually perfect because it allows me to run the Windows applications, and it also allows me to draw on the screen. Okay, so ABC, we have A, B, and C. Same thing. So going from left to right, since everything's the same, so A and B first with an AND gate, and then you connect it with another AND gate, and we're done. Okay. Now the next one, this is where things are now a little different. Notice that we have an AND operation and an OR operation. Okay. So this is where precedent order comes in. Precedent meaning that that you have to do certain operations before others. So if we were just dealing with regular algebra, which operation do you do first? Multiply or add?
Multiply.
Multiply. So in this case, we want to do these 2 first, right? So this would be A and B, and then you stick the result into an OR C. Okay. Now the next one is going to get tricky because now instead of being left to right, we now need to prioritize. Because we want to do AND first, this needs to be done first, right? So it's B and C has an AND gate between them. And then you take the result from A or B, or this output, okay? Everyone got that?
Could you explain that again?
You have to do B and C first, right? Let me draw the other alternative. The alternative would have been this. This is the wrong one. If you went from left to right, you would have drawn this. This would have been the wrong circuit. You know why? Because looking at this expression, which needs to happen first? AB or BC?
BC, right? I got it.
Got it? So that's why we did BC first and then connected it with an OR to A. All right? So this is the right circuit and the other one's the wrong one. All right, so let's take a look at some of the other rules of precedence, like which ones need to happen first. So precedence order, anything within parentheses needs to be done first. If you see a parenthesis, it means that needs to be done first before things outside the parentheses. Number two is really not second, it's actually the same, holds the same level, is not implies parentheses. So for example, if I have A or B, not, and C, this whole thing, A or B, implies a parenthesis around it, right? Anything below the not is implied to be part of the within parentheses, okay? So anytime you see a not, it usually implies there's parentheses around it. All right, so once all the parentheses are taken care of, you have no more parentheses, then the next operation you do all the AND operations. Once all the AND operations are done, then you do the exclusive ORs. And then you finish with OR. OR is always done last. All right. Okay, so with that being said, I'm gonna copy this. I want you guys to give you guys a good 10 minutes, work on these problems, all precedent order problems, to see what kind of circuit you end up with. Okay, so give you a good 10 minutes to work on this.
We're supposed to draw these out?
Yeah, draw these out.
Hello, Professor.
Yeah.
I'm currently in the library right now, and they're about to close in probably like 5 minutes. When is there going to be a quiz today, or?
Oh no. Oh no. Oh, okay. Yeah, guys, don't worry about that. The quiz, I think we mentioned it. The quiz is really not a quiz. It's just going to be some problems taken from our work set that you just plug in the multiple choice answer for. So I'm going to post it up over the weekend, and you have all week next week to do it. Literally, it'll just be like a test. You know, you sign in, and you'll have like unlimited time to do it. And it's just 3 questions. You answer it, and again, they're multiple choice, and they're taken right from the worksheet. You select the right answer, submit it, you're good to go. Easiest 5% you're ever going to get in life.
Thank you, Professor.
Okay, no problem.
Oh,
all right, you guys.
Question
Yeah.
about the midterm. So for our final score, we just divided by 4, right?
There's no
Since it was out
dividing.
of 400.
I wouldn't. Yeah, wait till your final grade, because right now it's still there's no score yet because the class is current.
Oh, okay. Thank you.
All right. So work on this problem. Try to get this done, and then we'll go over and do these. So draw out the diagrams. Okay, so let's we got enough time. Let's do this together. All right, so the first one is really simple, right? Because they're all the same sign, A, B, C, and there's no parentheses involved. So this is straightforward, A, B, C, and it's going to be A and B and C. Okay. Next one has a parenthesis there, so it says B and C needs to be done first. Okay, and then the result is put and with. All right, so both of these, A, B, C, right? Both of these are the associative law, right? Meaning that I can do A, B first and C, or do B, C first and connect to A. I'll end up with the same truth value. So this just demonstrates what I said earlier, is that this equation doesn't mean they're the same thing. It means that they'll reduce to the same result, either true or false, but the actual way they do it is different. So if you look at these two diagrams, they are not the same diagram, are they? So they're like sort of like mirror images of each other. Okay, so with that being said, it is that the Boolean expression is used to describe the circuit. So this describes this one, and this describes this one. They have two ands, you'll end up with the same result, but they describe a circuit that looks different. All right, so that's the difference there. All right, let's do the next one. All right, we have A or B or C. All right, so looking at this, doing precedent order, this needs to happen first, right? So we have A, B, C, and D. C and D needs to happen first. After that's done, then all that's left are OR operations. So since everything's OR, we move from left to right. So it's A or B is done first, and then connect it to with an OR to the result there. Okay? Any questions on this one? All right, next one is we have an AND operation in the middle, so it means these two are done first. So we have A, B, C, and D. So these two are done first. And now that after it's done, all that's left are OR gates. So everything's an OR, so it's going to be from left to right. So it's A, or, this result. And then this combines into one big expression, and then combine that with OR D. All right. Any questions on these two? All right, let's move on. Hey, I'm just curious. Is that guy who was in the library? Are you still there, or he got kicked out? Well, I guess he left. Hey, does anyone here study in the library? Just curious.
Yeah, they let you
I
stay
do.
even if they close.
Yeah.
No, it's all right. I was there years ago. I haven't been in the library in a long time. Is that guy who jingles the key still there? Like when it closes, he starts walking around jingling his keys.
I think he was in a public library because the Queens College Library closes at like 11 o'clock.
Oh, okay, got it. We're not talking about the Queens College Library, right? So wait, do any of you study in the Queens College Library?
Yeah, I don't think that guy's there.
That guy's not there?
Damn. And I
Do
didn't
you know who I'm
see
talking about? I think the guy just walks around, like starts jingling his keys, closing, he starts jingling really loud right next to your head. Makes you want to get up and punch him, No, right?
I don't
You guys
think
don't know
he's
who I'm
there
talking
anymore.
about. All right. I
know
didn't
he's
punch
not
him,
there.
but I can imagine someone punching him because he's just very annoying the way he did it. No, he just walks right next to your head and starts jingling his keys. Like it's not one little key, it's like a huge huge ring of like maybe like 30 keys on it. It's like crazy the way he's like walking around jingling that.
I
Alright.
once did punch him.
Huh?
I once did punch him.
Oh, so do you know what I'm talking
No,
about?
I'm just kidding. No, I have no idea, but
All right.
I was just making a joke.
Oh, that's probably why he's not there anymore. So I punched him. All right, let's do the next one. All right, so the next one looks like there is a not operation. So that means that whole thing needs to be done first. So we have A, B, C, and D. So left to right, we go A or B, that connects to C, and that whole thing has a not, right? And then once you do that, then it's just connected to D with the AND. Okay? All right, so the last one, you look at it and say, hey, wait a second. There's A is there twice. Is that a typo? And the answer is no, it's not a typo. Because in some circuits or inputs, your variables could be used in more than one gate. So in this case, if you did this, A, B, C, D, A, and you took A again, then that's wrong because it's not a separate input. It's the same input. So the question is, how do I reuse A? How do I wire it so that A can be used more than once? So what comes down to, again, let's start off from the precedence. We got the A and B has to happen first. So we do this. And then everything's OR, right? So OR C. And then the result is OR A. So A goes into, basically when this is done, it's this or A. So A is on the bottom of this gate. It's down, needs to be down here, right? So what we do is we go to A, and you'll see it written, drawn like this, a circle. A dark circle on a line means that the line is connected or split at that point. So we have this, we come down and we go around and we connect. And there you go. So very important is that to note, I'm going to highlight this. These are not touching. All right, even though it looks like they're connected, they're not. They're going around it, over it, under it, however you want to think about it. But A and that line B and line C are not touching. Okay. However, this is touching. See a dark dot there? That means that A is connected and split at that point. So A comes in here and it goes down here. So that's why A is used twice. All right, does that make sense? All right, so let me give you one to do that's not on here. Let's just make sure you have this. Let's do A and B or C, exclusive or D. Okay, and let's do there we go. So do that one. Give you a minute. Okay, guys, let's do this. All right, so we have the not. So that implies there are parentheses here, right? So that means parentheses are done first. So we have A, B, C, and D. Okay, this is or, and put a not. All right, so now that this is done, then it comes back to, this is done. Now it's precedent order again, right? So and has to happen next. So we do this and once this is done, then it's exclusive or with a D. That's it. Okay. All right. Any questions?
Professor, when there's like a plus B plus C, like we do it left to right, but it doesn't really matter, right?
It does, because if it doesn't matter, then how do you make the distinction between, how do you distinguish, if you say it doesn't matter, then the problem will be, then how do you distinguish between this and this? Right?
Well, aren't they logically equivalent though?
Yeah, but if you have to describe what the circuit looks like, do you see my point? You're trying to describe what the circuit looks like.
Right. Okay.
All right, so it does matter.
That's fair.
All right, any other questions? All right, see, that's good, because now we're going to do the exact opposite. Now you're going to get a circuit and you're going to try to describe it. All right, so let's very quickly go on the last slide is, how do we describe a digital logic diagram, right? So coming back here into our little example here, well, let's see, let me get a new screen. So let's just say the example I just drew, how do we make the distinction between this versus this? Right? How do we make the distinction? They're all OR gates. Well, what you do is you start on the left, A and B, and one gate at a time. So here, let's just say after this gate is done, this is A or B, right? So by the time it gets up here, over here, it's going to be A or B is on the left side, or C is on the other. All right, so now let's look at this diagram. Over here, this is B or C, right? So by the time it gets up here, on the left, it's A, and on the right of the OR is going to be B or C. Okay, so does that hopefully describe in more detail what we were talking about earlier about, does it matter what order you do it in?
Right, but these have parentheses. Do the parentheses?
Yeah, put the parentheses in, because without the parentheses, how would you do the one on the right? Right? With the parentheses, it makes it very clear that this is this guy and this is this guy.
But doesn't the order of the,
well, arguably you can say, yeah, you could, this is the same, yeah. But on the right hand, you have to have the parenthesis. Without it, you can't describe it.
yeah.
You understand? So there's no, if you put the parenthesis here, does it really hurt? No, it's fine. It just makes it more clear. You got it?
Yep. You need it on the right side, but not on the left.
Correct. And if you put it on the left, yeah, if you do it on the left, it doesn't hurt, does it? It's going to end up being the same thing. All right. So give you guys now a more complicated one to do. You have A, B, C, D. Okay, there you go. Give you a minute. Let's try to figure out how to describe this circuit. Sorry about that. I stepped away. All right, let's do the last one. So last problem is, where is it? It's odd. All right, so with this, at this point, it's A exclusive or B. And then over here on the left, it'd be A exclusive or B in parentheses. Or let's see on the right-hand side, let's work our way up. At this point, this is not C. And at this point, this is not C and D. So put it all together. This is not C and D. Okay, did you guys get this?
Yep.
All right, so it's very straightforward. It is that you just go through, starting from the inputs, you go one gate at a time, and then name that gate or name that expression up to that point, and just keep building up one piece at a time until you get to the very output, and you'll put it all together and you have your answer. Okay. All right. With that being said, guys, any questions?
Yeah, Professor, that last parentheses is implied too, so you didn't need the like the C and D because the multiplication is
Right. So just put it in there for clarity, because you don't lose any points for doing that.
gotcha.
Okay. All right. Any other questions? All right. If not, then thank you, everybody. Have a good weekend. And just again, I'll post the worksheet / quiz up over the weekend. And again, you have all week to do it. You can sign in anytime. Okay.
Professor, I have a question.
Mhm.
Are we able to see the problems on the test that we got wrong?
Yeah, you make an appointment with me to go over that.
Oh, okay, that sounds great.
Okay. Right.
But
Anything
I
else?
have a question.
Yeah.
Do you have an email address?
It's on a syllabus.
But I don't know how to use school email. Do you have Google email?
You have to use it. You know what? Sorry, you're gonna have to figure out how to use a school email. All right. I don't. How do you not know how to use a school email? That's
Yeah, I don't know. I just forgot my school email password. Like,
okay. So you need to go into Blackboard and look up my email there. Okay. So this is something you're gonna need to learn to do because you're gonna be in college for another 2 years. I think you should figure it out.
okay.
I'm sorry to be harsh, but this is something that's not really an excuse that you don't know how to use your email. You're a computer science student. How do you not know how to use your email?
I may send you the worksheet tomorrow. Is that okay?
No, because you're not turning it in. Have you been attending class? Because you
Yes.
seem you have. Okay. Okay. So what do we say about the worksheet?
Do you see it today? I joined late.
No,
Okay.
we said it a couple times already. It's not just today.
Oh, I forgot.
All right. You know what? I don't want to put you on the spot, nor I see your name, so I don't want to even see what your name is right now. Okay? Because my opinion is not very high at this point. So watch the video of this class. All right. You're not turning in the worksheet. It's going to be a quiz. So the first thing I would do for you is try to get into your email and then try to email me with whatever questions you have. Okay.
Okay.
All right. Have a good one. All right, guys. Sorry about that. Have a good night. Have a good weekend. I'll see you next Monday. All right. Bye-bye.
Thank you, Professor.
Hey, Professor.
Yeah.